Hello everybody, welcome into another lesson. So today we're going to talk about medians, altitudes, perpendicular bisectors, and then we get 4 new theorems that we're going to prove today. So we're going to talk first about the median of a triangle. The median of a triangle is simply a line drawn from any vertex angle of a triangle to the midpoint of the opposite side. So in triangle ABC, we have this line in blue drawn to the midpoint of BC. Why don't we call that midpoint X, okay? We'll call that X. Well, when this line is on the midpoint of the opposite side from the vertex angle, that's the median. As you see, BX is congruent to CX. It does, by the definition of midpoint. AX, therefore, is the median of triangle ABC. So, that's a median. You can kind of think of it like the median of a road. It's in the middle of the road, usually. Next, we have what is called the altitude of a triangle. So, let's talk about the altitude of a triangle. And in an acute triangle, the altitude is drawn from, let's do ABC here. ABC, right? Okay, so it comes from a vertex angle of the triangle to the opposite side, and it forms a perpendicular line with the opposite side. We'll call this X. That line in red, AX, would be the altitude of this triangle because it goes from a vertex angle to the opposite side of the triangle and forms a perpendicular line. So we can say AX is the altitude of triangle ABC. Now, something else to note, that in an equilateral triangle, which would also be equiangular, the altitude in an equilateral triangle is here, D, E, F. We'll call this blue point Y. In an equilateral triangle, the altitude bisects the opposite side, so it's not only the altitude, it's the median. It forms both a perpendicular line with the opposite side and it intersects the opposite side at its midpoint. So therefore it would actually be the altitude and the median in an equilateral triangle. These are for acute triangles. And this line actually here, the dy, would get to, it's going to be one more thing which we're going to talk about in a minute called the perpendicular bisector. It would also be that, but we'll talk about perpendicular bisectors in just a minute. Now let's talk about right triangles. Let's talk about those here. Alright, GHI. Okay, so we have triangle GHI here. In a right triangle, often the leg that's standing up is considered the altitude of a right triangle. So GH is not only the side of this right triangle, it's also the altitude of the right triangle. And then, also with right triangles, if you draw, let's see, this will be a right triangle again. We'll call this JKL. This will be triangle JKL. Okay. You can actually draw the altitude over you can draw an altitude from the right angle to have it touch lines J and L, we'll call this point Z. We'll call that point Z here. KZ could be the altitude of triangle JKL. So for two instances, you have in a right triangle where the altitude is actually one of the sides or one of the legs of the right triangle. In the third instance, you have the altitude of a right triangle inside the triangle, such as with triangle JKL, you have KZ. Alright, and then we need to talk about obtuse triangles. Now, in obtuse triangles, the altitude, well, let's label some points here, right? We'll call this here up north the top point, point M. This will be N. This will be O. Now, in an obtuse triangle, the altitude in 2 of 3 cases is an auxiliary line. That dotted line is called an auxiliary line, meaning it's not natively part of the triangle, but it's used to aid you in determining what the altitude is. Okay? And the altitude, we'll call this W here at the bottom of the red here, where it forms that right angle. The altitude itself of an obtuse triangle forms a right triangle outside of the obtuse triangle. So MW would be the altitude of triangle MNO, and it forms a separate right triangle MWN. And then, of course, you could end up having an obtuse triangle like we just had here, where, let's see, let's call this PQR. We'll call this triangle PQR, another obtuse triangle, where you actually have an altitude right here inside of the triangle. We'll call this V. So QV could be the altitude of triangle PQR. You can have them inside the triangle, but in an obtuse triangle, you also, and often with an obtuse triangle, you want to get used to seeing the altitude outside of the triangle, forming its own right triangle. So these are all examples of altitudes of triangles. Next, we will move on to the perpendicular bisector. And I'll illustrate with an example of that. Okay, let's begin with perpendicular bisector. Perpendicular bisector. That's a big one. We get to talk about perpendicular bisectors here. This will be point J, this will be point K. Alright, then we'll draw this in red through here at point M. This will be line L. This will form a right angle here. And then these two will be congruent. Okay. So the perpendicular bisector of a line, ray, or segment is such that the line is it's another line, ray, or segment perpendicular to that line, ray, or segment. Perpendicular in the sense that it forms a right angle, right? But it also bisects the segment it's perpendicular to. So line L is perpendicular to JK. Let's establish that here. So we know L is perpendicular to JK, right? And then, not only that, it intercepts that segment JK right at its midpoint. So it's both perpendicular and intercepting it's a segment bisector too at the same time. In other words, this would make JM congruent to KM, since it is the perpendicular bisector. And you know how we just talked about in equilateral triangles, how the median and the altitude are the same in an equilateral triangle? Well, those both are also the perpendicular bisector in an equilateral triangle. So those are also important to note. Okay, now I have 4 theorems here we're going to talk about. Well, 2 theorems, another definition, and then 2 more theorems. So let's talk about, I'm going to call these the perpendicular bisector theorem. The perpendicular bisector theorem. It's going to be a 2-parter, kind of like the isosceles triangle theorem, how there were actually 2 different theorems tied into that. We'll call this the perpendicular bisector theorem. It states that if a point lies on the perpendicular bisector of a segment, then the point is equidistant from the endpoints of the segment. Alright, so the first part of the angle bisector theorem states that if a point lies on the perpendicular bisector of a segment, then the point is equidistant from the endpoints of the segment. So let me illustrate that real quick here. So let's say that I have, we'll do line JK again here, right? And then at point M, I'll put here point N, right? Well, line MN is the perpendicular bisector of JK, okay? What this theorem is saying here, that this point N, which lies on the perpendicular bisector of the segment, is equidistant from J and K. So, in other words, I can draw lines here from J to N and from N to K, and Jn and Nk would be congruent to each other because N is equally as far from J as it is from K. And you can actually use triangle properties to prove this. So that's what we're about to go ahead and do right now, actually. So let's go ahead and do a proof, okay? That'll be point X. This will be point A here on line L. All right, we can establish that line L is the perpendicular bisector of line segment BC at point X. Then we're going to draw lines from A to B and A to C. All right? That's how we're going to solve this. So what we've been given to prove this theorem, we are given that L is the perpendicular bisector of BC we're also given that A is on L. What we need to prove is that AB is equal to AC. So basically, we have here line segment BC with line L perpendicular to line segment BC, and it bisects it at point X, meaning BX and XC are congruent to each other. So in other words, line L is the perpendicular bisector of line segment BC, and point A lies on point L. We're going to try to prove that A is equidistant to B and C. That's why we have AB equals AC. So let's go ahead here and let's set up our proof. And this won't be as bad as you think. Alright, so statements. Let's start with our given information. L is the perpendicular bisector of BC. That piece was given, and then A is on L. The reason it was given to us. Okay. And then we have here, if we have a couple things we can conclude. That angle AXL and angle AXC are right angles. We can also conclude that BX is congruent to CX. How could we conclude that? Based on the definition of perpendicular bisector. So the definition of perpendicular bisector enables us to conclude that angles, did I say AXL? I'm sorry, I don't know where I got L from. Should be AXB. We can actually conclude that angles AXB and AXC are right angles, as well as BX being congruent to CX by the definition of perpendicular bisector. Then we also have, next, where are we going to go from here? So we know we got some right angles here, right? We got congruent sides. And then isn't it true then, if we're basically going to base this on a triangle with a diagram, that AX is congruent to AX? That's of course by the reflexive property. So AX is congruent to AX by the reflexive property. So now we have right triangles, we have a leg and a leg congruent. We can actually go ahead now and conclude that triangle ABX is congruent to triangle ACX by the LL theorem, the leg-leg theorem, which we can use for right triangles. So by the LL theorem, triangles ABX and ACX are congruent, which would then leave that AB equals AC by CPCTC. Corresponding parts of congruent triangles are congruent. So we have here AB equal to AC by CPCTC. So let's go through this proof again. We were given line segment BC with line L as the perpendicular bisector to BC, which was part of our given information, and we have that A is on L. That was given to us. And then based on the definition of perpendicular bisector, we can conclude that angles AXB and AXC are right angles, and that BX is congruent to CX. And then by the reflexive property, we can say that AX is congruent to AX. By all what we have so far, by the leg-leg theorem, we can conclude that triangle ABX is congruent to triangle ACX, which last but not least leaves us to AB equals AC by corresponding parts of congruent triangles are congruent, or CPCTC. Alright, let's do what's next here. This is another part of the perpendicular bisector theorem. The other part is if a point is equidistant from the endpoints of a segment, then the point lies on the perpendicular bisector of the segment. So we had the first theorem of the angle bisector theorem. Now we have part two, which is simply the converse. This states that if a point is equidistant from the endpoints of a segment, then that point lies on the perpendicular bisector of the segment. So we'll get into a proof with that real quick. See what we got here. Let's see. Let's draw this nice triangle here. We have triangle A, B, and C. All right. And we are given the fact that AB is congruent to AC. So here's what we're given. We are given that AB equals AC. What we have to prove is that A is on the perpendicular bisector of BC. So now we're proving the converse. This time we have that AB equals AC. A is equidistant from B and C, in other words. So we have to prove that A is on the perpendicular bisector of C. Well, let's go ahead, let's set up our columns. Let's start with our first given statement here is that AB equals AC. The reason for that is it was given. Alright, this type of proof's a bit different. So what are we going to do here? What do we do here? You can draw what's called an auxiliary line. It is permissible to do that. So at point A, we are going to draw an altitude to BC. So an altitude means it meets the side opposite that angle and it's perpendicular to that segment. We will call this here point Y, where BC and A meet, okay? Now, we can actually say next that AY is perpendicular to BC by the definition of altitude. So by the definition of an altitude, AY is congruent, did I say congruent? Forgive me for that. Dang it. I meant to say AY is perpendicular to BC. By the definition of altitude, AY is perpendicular to BC. So now we've split this triangle into two right triangles, right? Which, why don't we state that triangle ABY and triangle ACY are right triangles. Well, by the definition of right triangle, since they're both triangles with right angles in them. So we can now soundly say that triangle ABY and ACY are both right triangles by the definition of right triangle, okay? So now we have two right triangles. We have the hypotenuse is congruent in each. What else? Well, isn't it true that AY is congruent to AY by the reflexive property? So AY is congruent to AY by the reflexive property. So now we have a leg and a hypotenuse in each triangle congruent. We can actually now say that triangle ABY is congruent to triangle ACY by the HL theorem, the hypotenuse leg theorem. So now we've proven these two triangles congruent. Alright, so what else then? If we've proven these two triangles congruent, then wouldn't that have to mean, since BY and CY are corresponding parts of those triangles, that they're congruent to each other? So we can put that in our diagram now, since we've proven the triangle's congruent. We could say that BY is congruent to CY by CPCTC. So now we have not only that AY is perpendicular to BC, but point Y is the segment bisector, and A lies on the perpendicular bisector of BC by the definition of perpendicular bisector. So we can now prove that A lies on the perpendicular bisector of BC by the definition of perpendicular bisector. So let's go through this proof again here. We were given triangle ABC, and to start with, all we were given is that AB equals AC. That was our given. Next, we are able to draw an auxiliary line. We drew line AY. It's the altitude of this triangle, which means AY would be perpendicular to BC by the definition of altitude. And then that has to mean that triangles ABY and ACY are right triangles by the definition of right triangles, since both of these triangles have right angles. And then, of course, AY is congruent to AY by the reflexive property. And then we can conclude that triangle ABY is congruent to triangle ACY by the hypotenuse leg theorem. And then we can conclude that BY is congruent to CY by CPCTC, that corresponding parts of congruent triangles are congruent. Well, if you have two congruent segments here of one segment, that means point Y is the segment bisector of BC. Also at point Y, AY is perpendicular to BC. So therefore, A lies on the perpendicular bisector of BC by the definition of perpendicular bisector. So that one was a little more involved than the last one, but really not that bad. Okay, I got a definition here, then I have two more theorems that we're going to go over. Okay, so distance from a point to a line. We are now going to talk about distance from a point to a line here. Alright, so let's say we wanted to find the distance from point R to line AB, or line segment AB in this case, what have you, right? Well, the distance is the perpendicular line. It's the length of the perpendicular line leading from that point to that segment. So from point R to AB, we'll call this intersection M, where AB and R intersect. The distance from point R to AB is the length of this perpendicular line RM to AB. That's the distance. So for the next couple theorems we're going to talk about, we're going to be having perpendicular lines. That's how you would measure the distance from a point to a line, though, even in any real life setting. Find the perpendicular distance. Okay. I don't really have a name for this. We already have an angle bisector theorem, so I don't want to call it this because it's just going to be a general theorem. If a point lies on the bisector of an angle, then the point is equidistant from the sides of the angle. And let me draw an illustration here so I can illustrate that properly. Alright, what else does it show? Whoops, it doesn't show that. This would be point. Let me extend this a little bit here. I butchered that a little bit. As I said, I'm not the best at drawing. Alright, so what else do we got here? This is perpendicular, okay. So, in other words here, let's go over this theorem again. If a point lies on the perpendicular bisector of an angle, then the point is equidistant from the sides of the angle. So, here, ray BP is the angle bisector of angle ABC. Well, point P lies on that angle bisector. It's going to be equidistant from side AB and side BC. That's what that's saying. And you have the perpendicular lines here to measure the distance from ray BP to line to ray BA or ray BC. So that's what that's saying. Now we're going to go ahead and prove that theorem. Let me draw this a little bit better this time. This time I'll draw the bisector in red. There we go, that's in red. This is definitely point B right here. That's point A. This is point C. This right here is point P. This would be Y. That up here is X. Alright, so there we go. Let's see what we're given. We are given that I guess this is a point Z here, okay. We are given that ray BZ bisects angle ABC. Are we given anything else? We are given that P lies on ray BZ. We are given that line segment PX is perpendicular to AB. It's perpendicular to ray AB. Then we are given that PY, that segment, is perpendicular to ray BC. So what are we going to prove out of this? Well, we're going to prove that PX equals PY. Alright, so ultimately here, we're given this nice diagram with an angle bisector. We're trying to find the distance between P to AB and P to BC. We're given that ray BZ bisects angle ABC. We're given that P lies on ray BZ. We're given that line segment PX is perpendicular to ray AB. We should probably make that a segment AB and BC. Alright, we're also given that PY is perpendicular to line segment BC. We need to prove that PX equals PY. So, let's draw our columns here. Alright, so let's first start with the fact that ray BZ bisects angle ABC. ray BZ bisects angle ABC that was given to us. What that means is if ray BZ is the angle bisector of angle ABC, then angle ABZ would have to be congruent to angle ZBC, right? That's what we would end up getting, is that angle ABZ is congruent to angle ZBC by the definition of angle bisector. All right, what else do we have? We also have here that P lies on BZ, of course. We'll use the rest of the given information here. P lies on BZ, ray BZ I should say, and then line segment PX is perpendicular to line segment AB, and line segment PY is perpendicular to line segment BC. That's going to be given to us. Okay, now we have here that triangles PXB, so we can say triangle PXB is congruent to triangle PYB. Not congruent yet. And PYB. Triangles PXB and PYB are right triangles. Well, by the definition of right triangle. Which means next, then, we have here two right triangles. We so far have congruent angles. They both share leg BP, right? Leg BP. So we could say BP is congruent to BP by the reflexive property. So that would be step 5. The reason for that is it's the reflexive property. Which next, we now have an acute angle and the hypotenuse congruent. We can therefore now say that triangle PXB is congruent to triangle PYB by the HA theorem, the hypotenuse acute angle theorem. Those two triangles are congruent. And then last but not least, that's going to leave us to conclude that PX is equal to PY by CPCTC. So PX is equal to PY by CPCTC. Corresponding parts of congruent triangles are congruent. So let's go through this proof again here. So we had this nice angle ABC. We're given that ray BZ is the bisector of angle ABC. That's given to us. Now, if that ray is the angle bisector, then by the definition of angle bisector, that means angle ABZ is congruent to angle ZBC. And then we can use the rest of the given information in the third statement that P lies on ray BZ, PX is perpendicular to AB, and PY is perpendicular to BC. All that was given. And then we can say triangles PXB and PYB are right triangles by the definition of right triangles. Then by the reflexive property, BP is congruent to BP since both right triangles share the same hypotenuse. And then ultimately we can conclude that triangles PXB and PYB are congruent by the hypotenuse acute angle theorem, the HA theorem. And then last but not least, PX equals PY by CP/CTC. So that is that proof. I got one more theorem and proof, and then we're done with the lesson. Okay, what do we have here? This theorem, you guessed it, it's going to be the converse of the one we just did. If a point is equidistant from the sides of an angle, then the point lies on the angle bisector. So now we have the converse of the theorem we just talked about. If a point is equidistant from the sides of an angle, then the point lies on the angle bisector. And we're going to prove that real quick too. So let's draw another diagram here. All right, so sort of similar, but we're working in reverse this time. We're going to be working in reverse. Okay, what do we have here? We still have points A and B and C. That much is given to us. We have point P right here. That would still be Y. That would still be X. They even give us that we still have right angles here. Okay, so what are we given? We have been given that PX is perpendicular to ray BA. We have been given that line segment PY is perpendicular to ray BC. What else have we been given? There's something else. We're even given that PX equals PY. What we have to prove this time is that ray BP bisects angle ABC. So that proof looks like a doozy, but it won't really be that bad. So let's go ahead with set up our columns here. Final proof, everyone, then we're done with the lesson. So we have statements and reasons. Okay, so step one, we're given that Px is perpendicular to ray BA and that segment PY is perpendicular to ray BC. That, of course, was given to us. We'll get the other piece of given information in a second. I'm jumping ahead of myself today. That was given information, which then by the definition of perpendicular lines, that means that angles PYB and angle PXB are right angles. That's by the definition of perpendicular lines. Okay, which then means, since we have right angles, that means triangle PYB and triangle PXB are right triangles by the definition of a right triangle. Alright, now, since we've established that triangles PXB and PYB are both right triangles, doesn't it look pretty safe to say that BP is the hypotenuse for both triangles? Therefore, line segment BP is congruent to line segment BP by the reflexive property. Then we were given also for step 5, use our last piece of information that Px is equal to Py. That, of course, in step 5 was given. In fact, let's mark them on our diagram that they're congruent. There, we got congruency markers now. If we look at these two right triangles, you have a leg and the hypotenuse of each congruent to each other. So the next step is now to say that triangle PYB is actually congruent to triangle PXB by the hypotenuse leg theorem, or the HL theorem. You can say that. So that's great. Now we've even established that we have congruent triangles. So ultimately, we're trying to prove that ray BP is the bisector of angle ABC, right? We're almost there, but not quite. Not just yet, okay? Wouldn't it be true that angles XBD and angles XBP rather, and YBP are congruent if they're corresponding angles? Let's go ahead and mark those congruent. We can now say that angles, well, actually, let's say PXB. Angle PXB, no, not PXB, I said that wrong, forgive me. We want this to be the vertex. It'd be angle XBP is congruent to angle, let's say ABP. Because at this point we want to use the whole thing, because ultimately we're trying to prove a bisecting of angle ABC, the whole angle. So angle ABP is congruent to angle CBP by CPCTC. Corresponding parts of congruent triangles are congruent. So then, if we have two congruent angles here, that would have to mean that, for step 8, that ray BP bisects angle ABC by the simple definition of angle bisector. I better say definition of angle bisector. Alright, so let's go through this proof again here, alright? We have here again an angle ABC. And it's cut by ray BP. We're given that segment PX is perpendicular to ray BA. We're even given that segment PY is perpendicular to ray BC. We use that for statement 1 for our given information. Which, if that's the case, that means for statement 2 that angles PYB and angles PXB, both of those are right angles simply by the definition of perpendicular lines. Which then means that triangles PYB and PXB are right triangles by the definition of a right triangle. And then it's obvious that BP is congruent to BP since both right triangles would share the same hypotenuse. That's by the reflexive property. Then for statement 5, we're also given that PX equals PY. That was given, which allows us in step 6 to conclude that triangles PYB and PXB are congruent to each other by the hypotenuse leg theorem, the HL theorem. And then we can conclude that angle ABP is congruent to angle CBP by CPCTC. Corresponding parts of congruent triangles are congruent. Then last but not least, ray BP is the bisector of angle ABC based on the definition of angle bisector. So I know this was a loaded lesson, but these are very important theorems for future lessons. So the next lesson, we're going to move into quadrilaterals. We're going to talk about properties of parallelograms in our next lesson. So I hope everyone has a great night. Take care.